This is lesson 3.3, chemical properties. So let's start with group 0, which is the noble gases. The noble gases are all colorless gases. They're monatomic because they don't like to bond to anything, and they're unreactive. And why are they so unreactive? Remember, the noble gases already have that full octet configuration, so they're very stable. Group 1, the alkali metals. They're all silvery metals. They're too reactive to be found in nature. They form +1 ions. And the reason that they're called the alkali metals is because if they form, when they are in solution with water, they form an alkaline or basic solution because they produce hydroxide. So for example, if we put potassium in water, we're going to make potassium hydroxide, which is a base, and hydrogen gas. So please make sure that you write down these physical and chemical properties for the alkali metals.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
OK.
Good luck. OK, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
Wow, that is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it?
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
OK, John, go for it.
Warning! 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 Extreme danger! Clear the area!
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does.
Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.
Alright, let's talk about group 7, the halogens. So remember, the halogens are all diatomic. And why do they decrease in reactivity as you go down a group? Well, as you go down, remember, you get larger and larger and larger. And so your effective nuclear charge is going to decrease. So your reactivity will also decrease. So physically, the halogens are colored. and they go from gases to liquids to solids. So they're the only group that contains all three phases of matter. And they're very reactive. However, their reactivity decreases as they go down. And remember that they form ionic compounds with metals, but they can also be used to form covalent compounds with nonmetals. So halogens react with group 1 metals to form ionic halides. For example, sodium plus chlorine will form sodium chloride. But they can also participate in displacement reactions. So single replacement reaction, for example, potassium bromide plus chlorine will give potassium chloride plus bromine. And they also form insoluble salts, meaning precipitates, with silver. So silver ions plus any type of halogen ions will form a silver halide precipitate. As we go across the periodic table, the elements go from metallic to nonmetallic, because remember, metals are on the left and nonmetals are on the right. And this can be shown through the bonding of the period 3 oxides. So if we look at the oxides of period 3, so here's period 3, sodium oxide, magnesium oxide, aluminum oxide, and so on. Initially, you're going to form ionic compounds. So sodium oxide is ionic, magnesium oxide is ionic. And as we go across, aluminum oxide is also ionic. So as we go across, we have giant ionic structures, meaning lattices. But then, as we enter the nonmetals, we are going to form covalent compounds, nonmetals and nonmetals. So phosphorus and sulfur and chlorine all form molecular covalent oxides. In the metalloids, silicon dioxide is actually a giant covalent structure. So it has no edges. It just repeats after itself over and over. Silicon, oxygen, silicon, oxygen. So it's similar to ionic in that it creates this huge lattice, but it's actually a covalent compound. So here we have it. We have sodium oxide all the way over to chlorine oxide. And here's a summary of the bonding. And remember, ionic compounds will conduct electricity and covalent compounds will not. We can also look at the acid-base character of the period 3 oxides. So, metallic elements, the ones that are ionic in character, are basic, and the non-metal oxides, the ones that are covalent in character, are acidic, and those that are in the middle are actually both acidic and basic. So we use a special word for those called amphoteric.